Well, first off, good on you all for getting through that last section. I know it was a little bit tricky. It would have been so much easier if I could have sort of shown you things and let you hold things, and we could have actually um, done this in person. But way to go, you made it through. We just have one really short little burst of energy here for the next couple of weeks to get through a topic that, frankly, is going to impact your life in a lot of ways that you may not even realize quite yet. And for sure, for those of you moving on to statistics, this will be like the big deal in statistics. If you're not moving on to statistics, though, still probability is something that governs almost every day of our life in some way. And so I just want to give you a couple chances to look at some ideas around it. We'll do more certainly as we get into the advanced algebra, and certainly, like I said, statistics will do that as well. I want to show you an example of where this shows up, and I obviously we could use the virus if we wanted to, but we're all a little bit worn out, I think, with the COVID-19 issues. So instead, I'm going to show you a couple things that have to do with football. Because one day, football will come back, and we might actually watch football on television again. Maybe get to go to a game. So this is one of the more recent lists of odds, which are definitely associated with probability. Odds of different players in the NFL winning next year's MVP award. And you notice that our boy Russ is at 12-1. One guy, Patrick Mahomes, is a 4-1 odds, but Russ is at 12-1. And so the question is, what does that mean, 12-1? Well, really what happens here, and I'm kind of getting a little bit ahead of ourselves, but we'll talk through it, is that these numbers talk about the chances they're not going to win rather than the chances they are going to win. So these are considered odds against winning. And so like in Russ's case, where the odds are 12-1, that means out of every 13 chances, 13 seasons, 13 opportunities, he would not win the MVP 12 times. He's going to win it once. So it's 12-1 against him winning. And that would tell us that there's a 1 in 13 chance that he's going to win. 1 out of 13, which is going to become the basis of our look at probability. For Patrick Mahomes, you can see it's more like a 1 in 5 chance. 4 chances he loses, 1 chance that he wins. So 1 chance in 5. So that's one way of doing it. Here's another one, though. And if you have ever studied betting, and to be clear, I'm not trying to tell you to bet. By the way, little words of advice from me: only bet on something you can control. Don't waste your money betting on something like this. I mean, you have no control over it. I mean, that's gambling. Some people like to do it. As a math person, as a statistician, I can kind of convince myself it's not worth it. But if you're going to bet on yourself. All right. So what this says is that Russ is at plus 800. By the way, this has him much more likely to win than the last one. The plus 800 means if you bet $100, you'd win $800. In the other one, this one down here, if you bet $100, you win $1,200. So this one this one up here likes his chances of winning better than the one down below. You notice it goes Mahomes, Jackson, Russell Wilson, and then Watson, Prescott. Down here, you got Prescott up there actually pretty high. Sean Watson's not even on there. So anyway, this is where we see probability start to show up in the world around us. Now, what I want to do is I want to give you just a little glimpse of what probability is. And some ways we can work with it. Now, I have to assume at this point that you've seen some sort of introduction to probability and some idea of what it's about. But I'm not going to make any assumptions because I know, guys, I know you've had a really rough go the last 2 years when it comes to math. And I thought we were doing some pretty cool things in class, but here we are. I'm talking to you on a digital whiteboard over a video. So I want to give you a quick little review of what probability is about, and then we'll take a look at some characteristics. So probability is at its core a fraction or a ratio. It's a way for us to compare two values. So what are those two values? Well, these are values that you're going to have to count. So in the back of my mind, I'm going to remind myself that we have to be able to count. On one hand, we're going to have the number of possible outcomes. Okay? Total possible outcomes. For example, if you roll a die, did you know that one die is called a die and two of them are called dice? So if you ever hear somebody say, I need to go roll one dice, you can just sort of chuckle and like, oh, they don't know. You roll a die, you roll two dice. If you roll a die, there are 6 outcomes, right? Did you know how many outcomes there are if you roll 2 dice? It's tempting to say 12, isn't it? But it's 36 because it's 6. So the first one is 6 and the second one, 6 times 6. Okay, so that value goes in our denominator. This concept of numerator and denominator is going to become a big deal probably in the next section. So then what we want to know is also the number of successful outcomes. So that's things we want to have happen, and that number goes in the numerator. So like if I was saying I want to roll, still rolling a die, an even number, which would be 2, 4, 6. There are 3 ways that I can do that. Okay, so what that lets me do now is say this: find the probability of rolling an even number. Well, I think to myself, the denominator means there's 6 possible ways that I can roll and get a number. 3 of them are successes, and so I would reduce that to 1/2. Sometimes people will say that equals 50%, but the cool kids in statistics and probability say 0.5. But we can stick with 1/2, that's fine. So we're looking for number of successful or positive outcomes on top here, and the total number of possible outcomes goes here on the bottom, and it's a ratio between those two numbers. Okay. So with that, what I want to do is show you a little bit about how we handle 2 possible events. Okay, so we're going to let event A, and this is all going to be about rolling a die still. Event A is I roll an even number, which again is 2, 4, or 6. Event B is I roll a prime number. Remember your prime numbers? Well, remember 1's not prime, but a prime number is one who only has factors that are itself and 1. So in the case of rolling a die, the prime numbers would be 2, 3, and 5, because 4 and 6 have other factors. Okay. All right, so we have these things called event spaces. I'm going to actually make this a little bit cleaner now. These are event spaces. These are the numbers that represent successes in our question, in our event. And now what I want to do is I want to introduce you to the concept of mutually exclusive, in the sense of, are these two events mutually exclusive? So think about the word exclusive. Exclusive means to exclude, which means that they're sort of separate from each other. Mutually means literally from each other. So mutually exclusive means they're completely separate and they have no outcomes in common. So to illustrate this, let me make a nice big circle here. And I want to take a little bit of time to make sure this is really, really clear. So this is going to represent all the different outcomes we could have when rolling a die. I'm going to put the numbers 1, 2, 3, 4, 5, 6 in here. Check my colors here. So I had orange in the middle. Okay. So for event A was rolling even number. I can represent the event space by circling all the numbers in that event, 2, 4, and 6. If you go back here, you'll see 2, 4, and 6. And then what I have is an event space for a prime number, which looks like that, 2, 3, and 5. And then I ask you, are these events mutually exclusive? And the answer is no. Why is it no? Because of that guy right there. 2 is a result or an outcome that is a part of both event spaces. So because there's overlap between the possible outcomes, these are not mutually exclusive. Now, let me show you what it looked like if we did have mutually exclusive. We're going to let A be prime number, and B is going to equal the number 6. I'll make this very easy. And I think that once I draw this out for you, it should be pretty clear what I'm getting at. So 1, 2, 3, 4, 5, 6. Okay. So now the prime number event space looks like that. And the event B event space looks like that. See how there's no overlapping? There's no outcomes in common. So we say that these, yes, are mutually exclusive. Okay. So that's our first thing. Mutually exclusive means they have outcomes in common, or maybe they don't. Now, second concept I want to show you is that of independence. And it's funny, not in a ha-ha funny way, but sort of a sick and twisted way. It's funny how confusing mutually exclusive and independent get when you start getting into higher levels of statistics and probability. They don't have to be that way, but often they do. So here's what happens. If knowing one event has happened, okay, so we're still talking about two events here. if knowing one event has happened changes the probability that the second event happens. So if knowing one event has happened changes the probability that the second event happens, we say the events are dependent. As in, one event depends on the other one. If that doesn't happen, then the events are independent. So if knowing something about the first event doesn't change at all the likelihood the second event happens, then we have independence. So what I want to do is show you a quick example from the other page. Scroll down here just a touch. So this is my example right here. This is a bag of colored marbles. There are 4 green marbles, 3 red marbles, 2 blue marbles, and 1 yellow. Okay, so let me go back. I have this up on the screen. You're going to lose it here, but let me go back here, and I'm going to draw this. Try to draw it exactly if I can. I'll draw it like a circle now. And then what I'm going to do is I'll set up the colors exactly in my head. So I've got, I've got 2 blues, 4 greens. I'm trying to make them match like you even care where they are. 3 reds. This kind of guy I am, just trying to make it match. And then you go. Okay. So altogether 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 marbles. Now, I happen to really like green marbles. So I'm going to draw 2 marbles out, and I want 2 marbles. Whoops. I just want 2 marbles. I want 2 green. Okay. So what I like to know is what's the probability that I pull out a green marble in the first ball? Well, it should be pretty easy that it's 4 out of 10 or 2 out of 5 or 0.4. Okay, that's not very difficult because there's four green marbles and 10 total marbles. But now here's the issue. What if I don't put it back? So I don't replace it, which means like this marble is now gone. Now what's the probability of a green marble on my second draw? Well, if you notice, now there's only 9 marbles left. So there's only 9 left, and of those, 3 of them are green. So that comes out to be 1/3. So the very fact of knowing that the first marble I pulled was green changed the probability that the second marble is also green. Because it would have been 4 out of 10. I mean, the probability of a green marble was 4 out of 10, or 2/5. But because I knew something about the first marble, and that knowledge changes the probability, what we say is that the act of drawing 2 marbles without replacement is a dependent set of outcomes. So what does it look like if I solve the problem? I just replace the ball, which means I put this ball back. I picked it, but then I put it back. So now what's the probability of a green ball, number 2? Well, there's still 10 balls left and 4 of them are still green, so it's still 2/5. So in this case now, with replacing, we get independence. In the sense that knowing that I pulled the green ball at first doesn't matter because I'm going to put it back in. I'm still going to maintain this 4 out of 10 or 2 out of 5 probability. So as you start dealing with some probability problems, one of the things you'll come across is replacement or don't replace. Or don't replace. And you'll have to remind yourself that when you replace, whether it's marbles, cards in a deck, whatever it may be, when you replace, you'll have independent events. If you don't replace, you won't have independent events. So I'm curious about something here, and we'll wrap up the independence part here with this conversation. What about this one? What about Mariners win the World Series versus Russ wins MVP? That's a weird looking hand, so I'm gonna fix that. So I wonder if these events are independent or not. Well, first of all, we don't know if there's going to be baseball or football, so we'll get beyond that. We said we're not going to deal with virus talk here. But presumably, whether or not the Mariners win the World Series, and by the way, they're not going to win the World Series because they're really, really bad. But in fact, I have to notice, I found out they have a 1 in 300 probability of winning the World Series, and Russ's probability is 1 in 13. So the question is, what's the probability of both of these things happening? Well, we can say they're independent because there is no reason to think that Mariners winning the World Series or not will have any bearing whatsoever on what Russ does with the MVP. So the probability that both happen is just the product, that's multiplication of the two probabilities, which is about 1 in 3,900, about 1 in 4,000. So go teams, win the contest. Those events are not both going to happen. Now, Russ might win the MVP. Mariners certainly are not going to win the World Series. But this is what you can, this down here is what you can start to do once you have established events are independent. Okay, last concept. And I know this is getting a little bit long, but I think it's worth thinking about. We've talked about complements before. And to be clear, there are complements and there are complements. Specifically, there's complements, like complementary angles. These are not angles that say, my, you look lovely today, or you're a cute angle. By the way, that joke never gets old for geometry teachers. Not a complement, but a complement. And so here's another picture that you can see where you start to have this idea about circles and event spaces, and you'll notice that the spelling changes a little bit. It's the same spelling we use when we talk about complementary angles. And in fact, in a lot of ways, it means the same thing, because a complementary angle completes a triangle, right? But if I go back to the concept here, a complement completes. So in a right triangle, I don't have a right triangle. In a right triangle, you know, we'll have maybe 40 degrees there. The complementary angle completes the triangle to make 50 degrees. In a probability setting, the complement means everything else. That's it. It's like everything else except for what you wanted. So remember we had this event earlier where B was the event rolling a prime number. So we write this as B complement, and I'll make a note about this in just a second. B complement means rolling anything but. A prime number. So this would be 2, 3, 5. This would be 1, 4, 6. Okay. Now, what I want to mention about this notation is that your book does something super goofy. Your book calls it C for some reason. I'm not really sure why that notation is there. Typically, if you have an event B, then the complement is written as B with a, it's not like an exponent, it's more like a superscript, BC. So what really happens here is the probability of any event happening, which the probability can't ever be more than one. It can, like in this case, it's 1/2. The probability of the event plus the probability of its complement, by definition, always equals 1. And that means 100%. So a complement is going to be everything but what you're looking for. And I just want to clarify one thing. It's very easy to think that the complement, like if you're talking about getting a grade on a test, that the complement of an A is an F, and that's not true at all. The complement of an A is not getting an A, B, C, D, or F. It's everything else. So it's not like opposites or two extremes. It's what you want versus everything else except what you want. Okay, so to sum up, the 3 concepts I want you to know for this lesson are mutually exclusive, independent, and complement. Okay, and I will be back next week with one last lesson for you, one last video, and then we'll have a short quiz the full week after that, and that will be that, guys. We'll wrap it up. We'll call it a crazy year, and then we'll start thinking about another crazy year next year. So here are your 3 assignments, or 3 options for assignments. First of all, page 504, 5 through 9, or 6, and 16 to 21. Or I've got a couple worksheets. One is a worksheet just on mutually. It's pretty tough to find worksheets to just cover these very specific little concepts here. So this one's on independence. So I would recommend that you do option 1, but I want to give you a couple options as well. So you can do extra practice if you want to understand this. But this is the 26th, Tuesday, short week. So I'd like to have this all done and returned to me Friday, May 29th. And then we'll kick off June with our last lesson and be almost done. See you next time. Bye.